Hi, everyone. Welcome to our monthly Science of All Proteins seminar. My name is Bianca Dada, and I'm the Scientific Partnerships Manager at the Good Food Institute. For those of you who are here for the first time, welcome to our community. The Good Food Institute is a nonprofit think tank 100% driven by philanthropy, and our goal is to build a world where alternative proteins are no longer alternative. If you're looking to take a deeper dive into the science of plant-based, fermentation, or cultivated meat technologies, check out our open access resources at gfi.org/science. Today, I'm thrilled to be joined by Dr. Da Chen, GFI grantee and assistant professor at Purdue University, who will discuss how plant protein gels can be engineered to deliver targeted texture, mouthfeel, and nutritional performance. Dr. Da Chen joined Purdue's Department of Food Science in the fall of 2023, following a prior appointment as an assistant professor at the University of Idaho. Before becoming a faculty member, he completed postdoctoral training at The Ohio State University and Purdue University. He also spent approximately 4 years at the University of Auckland in New Zealand as a graduate student. His research program focuses on structural modification of plant proteins to advance the manufacture, accessibility, and consumption of plant-based foods. He investigates protein structure-function relationships from the molecular to product scale using techniques such as extrusion, rheology, microscopy, spectroscopy, and scattering. His work has been supported by federal agencies, organizations, and industry partners. Dr. Chen, thank you for being with us today to discuss your research on plant protein gels. I'll turn the floor over to you.
All right, thank you so much for the introduction, and I'm so happy to be here to share some of my research. So some of them was done when I was a postdoc, and some others was done when I was being a faculty member. So in terms of the plant protein gels, and we know that it's not only like a aggregate systems, but it also has a lot of other things we could work on for those complicated with the intermolecular structure. So my name is Dan, and I'm assistant professor in the Department of Food Science at Purdue University, and this is my email address. So in today's presentation, I'm going to cover a few things. The first is what's the plant-based hydrogels, basically the protein-based ones, and how you can like change the gel properties that using like protease minerals, mainly calciums and carbohydrates, as well as phenolic compounds. So some of them are actually exist in plant protein ingredients. So it really depends on how you like isolate the proteins. And so after we do a different formulations or different modification to the proteins, then how we gonna know their, the structures, function relationships, how we could like precise modify the proteins in order to get the textures or mouthfeel that we need. And when you add different like non-protein ingredients into plant-based hydrogels, so how that affect the digestibility. And I think this is going to be covered by today's presentations. So the main focus is on the proteins, calcium, carbohydrate, and phenolic compounds, and how that's actually affect the gel properties. And some of them that you can make it stronger, and some of them you can make gels much weaker. So we're gonna use a different type of techniques, for example, like rheometer, and to see the relative properties, and microscope that you can see the microstructures, and you could also use some scattering and some other techniques that including the simulations to see how that actually affects. So what is the plant protein based hydrogels? So this is the left picture is the pea protein gels that we did in the lab. This is a lab extracted proteins. So it's pretty like milky appearance. But if you get a commercial pea proteins and you make a gel, it looks a slightly different. It looks more turbid, and because the particle sizes are much larger and has a less soluble. So the most common way to produce plant protein based hydrogel is by heating. And basically you make a suspension first and you heat it at 85 to 95 for 20 to 30 minutes, or sometimes you can heat a bit longer. It really depends on the nature of the proteins you have. So after that, you will get, and then cooling down a bit, and you will get a gel. So that's the gel strength of the plant proteins. It really depends on where it comes from, and also depends on how you get them. So some of them you could get a very like self-supporting structures that if you upside down and the gels will maintain itself, will not flow down. But some others, they may probably flow down. So if you take a look, further look of the gels, and it's gonna have a different like aggregates. So those aggregates, they have different sizes. Some of them are big, some of them are not. And some of them are look like more a linear, look like, but some are others more like an aggregates. So the distribution or the proportions of different structural unit in the gels actually determine the bulk properties, mainly the rheological properties. Well, then the question comes, so how we know that what kind of aggregates form? So what makes the aggregate form? Well, that's another question. So my personal thinking is the interactions, the chemical interactions. For example, how much covalent bond inside and how much non-covalent interactions contribute. For example, is that a lot of hydrophobic interactions or is a lot of electrostatic interactions? And this actually decide the aggregate size and their homogeneity as well as the network continuity. And that's actually will result different like rheological properties, or we say hardness or softness. So this is how the gel look like, and it actually varies a lot with the source of proteins and with the like whether they have any salt, whether they have a what kind of pH used. So we're gonna talk about that later on. And so when we study the hydrogels, like plant protein hydrogels, so what kind of products that relatively relevant? So you probably know that the tubes, which is actually very common ones, they're basically made with soy protein and has some calcium there, and you can actually like change the hardness or like the softness of the tubes that you can see in the supermarket. You have the soft ones, you have the firm ones, you have the medium ones. So you can change the concentration of the calciums and make a different firmness. So you can also see some yogurt, right? The plant protein based yogurt. You can produce this from fermentation. You can also produce from some other methods. Basically, you're more like a gel systems. I think one challenge for plant-based like yogurt is how you're gonna keep the water. You're gonna have good water holding capacity, so the water will not be leaching out with time, and that is actually widely seen in yogurt-based products. If you leave there in the fridge for some time, for example, a week or even a few days, you will see that there have a phase separation. The water will leaching out. So that's mainly because that the plant proteins they have a relatively weak water holding capacity. So you're gonna kind of figure out how you could hold more waters in the gels, so they will not be coming out of the with the cells is formed. So the other is plant protein blocks. Basically, this is more like a cheese block that you can actually get the proteins, right, and increase the concentration. So you will, and then press a little bit, so you'll get those blocks. And other type of hydrogel is, for example, plant-based meat. We probably don't think that is a gel. Actually, it does. Because you have a high solid content, so that's why it looks like a hard gel, but it actually is a gel. And the other type of products is the protein-based energy gels. So when people go to gym, so they want to get some supplement, protein supplement. So before it was just like powders, right? You make a powder, it's suspending water, you will get a like a drink. But now for the protein gel, you will get much better, a much higher concentration of the proteins. So you don't have to take too much of those water when you have the proteins. And this way, you will get more proteins and less stomach full. But in order to have those type of products, you want to make sure that the proteins will not be formed too hard gels. Because, for example, meat analogs, it has about 20-35% of proteins. Depends on the formulation used, but this high content of proteins will make hard gels. So how are you gonna weaken the gelling capacity in certain applications? For example, the high protein energy gels. How you get a flowable with the system, same time you have a high protein content. So we always like talking about how we could make gel stronger, but sometimes for certain applications, we really want to make gel to be a little bit fluid and weaker, right? This is one example. And other application that probably know about is dysphagia gels, that when people have the swelling issues. So how you get a weaker gels, high proteins, and more fluidable. So they could be has no challenges or difficulty when swelling. So how the gel is formed, and we talk about that because that you have a liquid and you heat it up to form a gel. That's what we call a heat form gel, which is one of the most widely used and most produced. So the process during the heating up of the gel with a like pea protein suspension or some other protein suspension is a different stage. I would say, like, if we control the heating rate and cooling rate, and we can monitor the change, those changes mainly because of the protein aggregates. So we did some work before that that we published in Hydrocolloid in 2022. So we do a in situ studies. Basically, we monitor the size change of the protein aggregates during the gelation process. So first we heat the proteins and then we'll see the G prime and G double prime change, which is the storage modulus and loss modulus. So we heat it up and we hold for some time, basically about 20 to 25 minutes, and then we're cooling down. So surprisingly, we have some very interesting findings that protein aggregates probably not always happens during the whole process. Most likely the aggregates stops in those in the beginning of the hold period here, which is here. So if you look at the rate of gyrations, it's pretty, you don't see much aggregation here, but it will start to suddenly aggregates in like about 25 minutes, which is about in here. And then when the aggregates reach a certain size, it did not further for larger aggregates, which is very interesting studies. So we always believe that it's going to be like continuous aggregates, but from these studies, and so we can see that this is probably not the case. And when you heat proteins, and so when the proteins start to unfold and aggregates, so the system viscosity going to increase. So when the viscosity is pretty high, then protein movement, like how easy they move, probably it's going to be much harder because they're more viscous, they're harder to move, and the proteins will not be able to, the smaller aggregates will not be able to move to a certain distance to aggregate with another aggregate to form a larger one. So in this case, during the cooling process, we say instead of they form a lot of aggregates, most likely is just because you have more molecular interaction happens. Most likely the electrostatic interactions and hydrogen bondings, because those interactions are actually weakened with temperatures. So when you drop down the temperature, and those kind of interaction will increase. So that's why you will see a higher G prime and G double prime in the cooling phase. So we talk about molecular forces a little bit in the previous slides, and so basically the protein gel, their strengths, I always think is how we could link that to the molecular interactions, because I'm like a chemist, right? I'm a food chemist, so I always want to see what kind of interactions, what kind of molecular forces could contribute and change their interactions. So the reason that the plant proteins gels they are relatively weak compared to the animal proteins, well, this sometimes is not a bad thing. Really depends on applications. If we look at the plant protein, so this is one of the proteins that mainly exist in peas. So the pea proteins, and you can see that they are pretty large molecules, about 250 to 300 kilodaltons. Sometimes they're even larger, and they have 6 different subunits. And if you take one of the subunit out, and that's what you will look like. So in this subunit, you can see different colors on the surface. So the blue ones mainly represent the hydrophilic, while the red ones are more about hydrophobic. So you can see that they have quite a lot of the red areas on the surface, which means that the surface hydrophobicity of plant proteins, at least in here, the pea protein, they are pretty high. They're not as a smaller protein, animal proteins that we see, they are very hydrophilic. So that's why sometimes you do see a low solubility of of P proteins. And besides the surface property, I mean, the sizes is here another. So when two protein molecules comes together, because they are very large, so the contact surface is going to be very limited. So that's why they will have, trouble to form a lot of interaction because their contact surfaces is limited. If they don't have a good contact surface, how are they going to interact? Because all of the molecular forces, pretty much all of them, is based on the like distances. If one protein and another proteins, their contact surfaces is not close enough, they will not be able to form those interactions. So what kind of interaction that it has in plant proteins is basically, like we say, depth of a band. That's mainly exist in animal proteins, but not in the plant protein, because plant protein normally has a very when you make the gels, they will have a very low proportions of covalent band, which is depth of a band. But they have quite a lot of hydrophobic interactions and electrostatic interactions, hydrogen bonds as well. So the sizes of the plant protein and the surface properties, so make them have relatively weaker interactions. So is there any way we could change it to modify the protein so they could have better interactions and possibly will make the gel stronger? This is one we published before, and again in hydrocolloid 2022. So we found out that if we use the alkylase, which is enzymes, right, a protease. So you add alkylase and you do very short time hydrolysis. So the reason that we use very short time because we don't want to break the protein to be very short, very small peptide. Want to maintain that it has a reasonable size, because if you break the protein to be much smaller, it's very hard for them to form a lot of long distance networks. So what we want to keep it relatively not as big as the parent protein. Still, they will have a reasonable size. Same time, they will have a much more available surfaces to interact. So we did that, and for 5% of P proteins, and we did a heating afterwards, which is 85 for 10 minutes. You will never get a gel using those kind of conditions because they are pretty very mild heating conditions, but you can get the gels at this concentration under this kind of heating. So which is, you can save a lot of material, same time you can save a lot of energy, which is, we say, a plant protein we want to make more sustainable. And that's one way to make a plant protein gel to be more sustainable. So we use 5% and protein concentrations, and we use a very short amount of heat. A short amount of heating time and lower temperature. Normally we'll do 95 Celsius for half an hour, but you can reduce it to 85 for 10 minutes. And we do make a comparison to 5% of P proteins that without hydrolysis, and even 10% of P protein, they will not be able to form a gel. They're more like a liquid or viscous liquid, but this one they form a gel. Then we're going to think what is going on. And first we measure the biological properties. You can see that this black square one here represents the storage modulus. It's actually changed from about, we would take one here. So it changed about from 2 to 150. So the gelling capacity actually increased about 100 to 50, 100 times, which is a really big improvement. So then we want to look at the structure, microstructure change. So what that happens? So we have the P protein here on the left. So we'll have the P protein hydrolysis that we started 2 different pH, but we found the pH 7 neutral pH works better. So if you heat up the P protein hydrolysis, that at 10 minutes you will form a lot of aggregates, but in here that you only see those smaller aggregates that actually scatter, right? They're not comes together. They're more like a segment. So in this way, when you have a lot of interconnected networks here, most likely you're gonna have a higher gel strength. So that's what we observed in the virology studies. Then we want to know why the proteins after hydrolysis, for a short time hydrolysis, they can aggregate better. So we did do a SH page to see, after we do the hydrolysis, you can see that their sizes are not that small, so about 10 to 20 kilodaltons. That's actually not very small peptides. We see pretty large peptides. And we also do the surface hydrophobicity, so they becomes more less hydrophobic, which means more hydrophilic. So that's probably like, we decrease the size to make it less steric hindrance. And at the same time, we do the hydrolysis, we make it more hydrophilic. So they probably have more like, charge based interactions or some other interaction as well. So we also look at the, we see those after hydrolysis, they are easier to form gel. Is that because that they are less resistant to heat? So we did do the thermal properties analysis. So you can see that there's slightly increases for the onset temperature and denaturation temperature, but there's decreases about the enthalpies, which means that the hydrolysis actually disrupt proteins and make them to be like they need less energy to fully denature. So then we want to look at what kind of molecular forces that after hydrolysis and they could facilitate formation of stronger gels. So we use the DGT, which is a reducing agent that that actually you can reduce the disulfide bond to be the cell groups, and we also do the like sodium chloride that could cover some of the charges. So we can see. We also did some other, analysis about other molecular forces, but we found that actually the disulfide band and also the electrostatic interactions are the ones who could maintain the gel structure better. And so from this study, we can see that after hydrolysis, we can increase the disulfide band and also the electrostatic interactions for the hydrolysis that makes them to formation of stronger gels. Then we did a further study about how we could apply those kind of gels. So we do the pea protein hydrolysis gels, and it looks 5% of concentration, it could form a gel. And this gel has a reasonable or a little weak with the strength. So how we could use that? So we did do a drying process, and then we add that to be used as a fat replacer because we think they're pretty soft particles. And so we did that, and we use those gels as the fat replacers, and we included into with the dairy products, most likely to be the we included into the like skim milk, and we will see how that works with the rheology trial and sensory evaluations. So we did do a very good comparisons about the pea protein under hydrolysis. So we did find out that this ones, the pea protein gels, has a very good fat replacer. They can make the fat-free cream to be very creamy. If you don't add this, that's how it look like. It's pretty hard, rigid. But when you have those pea protein gels inside, you will get a very good creaminess. So we did all of those tests, and some of them we published, but some others were still the submission or under review process. So this is one type of application that we think that how we could use the weak gels or hydrogels from plant proteins. And the other one that we think is besides the limited hydrolysis, because sometimes with the enzyme is quite expensive. And so what others cheap sources? And one example is calcium chloride. So calcium is one of the widely used minerals that could strengthen the plant protein gels. The reason that could strengthen is because it mainly facilitate the electrostatic interactions. So basically, you have the carboxyl groups, and then you have the calciums. I mean, this is positive charge, and then you have the carboxyl groups from the protein that you have the very strong electrostatic interactions, and that could help to make the gel stronger. So we did that for the pea protein hydrolysis, and we also did that for the pea proteins without hydrolysis. And you can see that when you increase the strength of the concentration of the calcium, you did see an increase to a certain point. But if you add a lot, for example, 25 milligrams, you normally the strength will drops. So the reason that is most likely it form a less consistent networks. So we did that for the we say the macroscope structures, right? I mean, when we want to know how those G prime, G double prime chains want relevant that to the macrostructures. So if you don't have the calcium, it's form like a porous structures. But if you have some of them, you will see a little bit more compact structures. But if you have too much, most likely you're gonna form a pretty large aggregates that does not have a very good networkings. The other question is, when we add calcium, it makes gel stronger. How that affects the digestibility? Sometimes because calcium is cheap, but if you add that much, will that actually compromise the nutrition property or the digestibility? So we did in vitro digestion for the gel samples, and so one is the pea protein gel, one is the pea protein hydrolysis gel, and you can see the so compared to the zero concentration of calciums, when you have more calcium to be added, they actually drops the you can see here, they actually drops the soluble protein content. Most likely, we say if you add calciums to be at least to the pea protein gels, to make stronger pea protein gels, most likely it gonna compromise the digestibility. So this is mainly because some calciums they could actually block some of the accessible sites from on the protein, so the digestive enzyme will not be able to get access to. So the other reason is after digestion we have those peptides, and some of the peptides they could form the insoluble complex with calciums. So most likely then you will get less soluble proteins after do the centrifuge. The another one is the pectins. So we talk about calcium. We talk about limited like hydrolysis with enzymes. But what about carbohydrate? So carbohydrate is another we say major nutrients. So in food. So how the carbohydrates like affect? So different carbohydrates they actually have a different we say results on the rheological properties. Some of them increases, some of them not. So that really depends on the charge on the carbohydrate. For example, CMC that they are that have highly charged and they are not be able to form stronger gel. Sometimes they're even weaken the gels. So this time we used the pectins. So we use low methyl pectin. The reason that we use low methyl pectin is because it has relatively higher charge, but it's not that very high, so relatively higher charged, and sometimes pretty linear structures. Sometimes they may have a little bit of branch, but most likely they're going to be the homogalactic rhonan, which is a linear with a polysaccharides. So we add different proportions to the pea protein suspension, and we heat up the ferment gel and see how that works for the G prime. There are two main interactions that for pectins and pea protein. One is electrostatic interaction that you have the carboxyl groups from the pectins, which is negative charged, and then you have the ammonium groups come from the protein that they have the positive charged. So those two will have the electrostatic interactions, while you also have a lot of hydrogens and OH groups from the pectins, and you also have a lot of OH groups from the with the like proteins, so they could have some like hydrogen bindings as well. When this happens, that we can see that that's a control. The black one is a control. When you have more pectins added, you will see that the G prime increases. So especially that you have 0.3 or 0.5%, you will see about like 4,000. You can make the gels that starting from less than 1,000 to be 4,000, which is a big increment. Then we want to know why, I mean, besides those interactions, so what we want to know is where are the proteins and where are the pectins? So we did a immunofluorescence study that you can label. We use the L19, which is an antibody that you can specifically bind to the pectins. So the green ones are the pectins, the protein ones are red. So you can see that for some pH that they do have a homogeneous distribution, while for some other pHs they are more like phase separations. You can see some regions they have more proteins, and some other regions they have more pectins. So they do have the phase separations, and those phase separations are various at different pH. So we talk about several strategies about gel and how to increase the gel strength. But is there any way that we could weaken the gel strength? There are, yes. So one way that we're thinking about is the deamidation. So we originally want to increase the gel strength by deamidation. The reason that is because when we deamidate proteins, most likely we're going to make them more soluble. So that has been well studied in the literature that when you are using what's the enzyme, or we call that glutaminase. So deamidation is basically that you change the NH3 groups to be the COOH group. Most likely you will make it more negative charge. So when you make the protein more negative charged, and they're gonna have a much better solubility at a neutron pH. So we think that if we increase the solubility of the protein in the suspension, then most likely we can increase the gel strength. That's the original rationale. But after we did all the studies, and it turned out to be opposite. So even though you have a higher soluble proteins in this suspension, you still not be able to get a stronger gels. So we did just like pectins, we do with deamidation protein first, and we make suspension and we heat it up, and we study the rheological properties, structures, and see how, and chemical interactions, to see how like the deamidation affect the overall strength. So this one we published this year in hydrocolloids as well. And so we have for example, we have the pea protein suspensions with and without deamidation. So first we want to study their suspensions, because their suspension properties also are relevant to their final gel properties. So first we do a time sweep that you study the viscosity over time, because we do a 60-minute deamidation. So we want to see how the viscosity change over the 60 minutes. And after the 60 minutes, we also did we say a different shear rate at the flow sweep, and to see that how the viscosity changes at different shear rates. So you can see that when you have more glutaminase, so PG500 is the glutaminase, and if you have more glutaminase there, it's gonna make the viscosity increases. So this increases mainly because that you have a smaller aggregates, you have more soluble proteins in the suspension, so they will increase the viscosity. So this is the same thing that that it has a higher viscosity when you have a higher concentration of the glutaminase. But when you increase the shear rate, the viscosity is decreases. So this is very typical shear thinning behaviors, that when you increase the shear rate, the protein molecules, they're gonna realign, so they will have less resistance to the geometry. You will see the lower viscosity. But the interesting thing that when you have deamidation there, you're gonna have a higher viscosity. But will the higher viscosity lead to a higher, we say storage modulus? So we're gonna talk about in the next slides. So in here, that after deamidation, we characterize the suspension a little bit further in terms of the degree of deamidations, because we add different concentration of the glutaminase. And we also measure the sizes, delta potential, surface charge, and prop surface hydrophobicity, as well as the degree of hydrolysis. Because some of the glutaminates, they may have the capacity to hydrolyze, and we just want to make sure that they don't do much to the hydrolysis. And this is their SGS page. So we didn't see much hydrolysis there, but we did see that the surface charge decreases that as we original proposed, because it removed the NH3 and make us to and replace with COOH, so it's going to be more negative charge. So you will see a negative increase in the delta potential. And when you have more surface charged, most likely the protein is going to be more hydrophilic, so you will see a less surface hydrophobicity. So this actually show a promising that probably deamidation could also increase the gel strength, but actually after we make the gel, we see different. So when you have, this is the control, you see the black ones, but when you have more glutaminase inside, you will see that there actually gel strength decreases. So even though you have more soluble protein, still the final gel strength decreases. And So we also did a stress relaxation studies that we develop an equation to fit it. So you can search this paper and find out the equation that we used. So we actually do a stress relaxations to see the deformation of the gels in addition to the oscillation. So, and then we get a different parameters. So for example, the relaxation time, which is one of the important. So if you have a shorter relaxation time, most likely you have, which means that the like the gels they're weaker. So when we have more glutaminous inside, you will see that they have a much shorter relaxation time. We also have some other parameters. So because of the timeline, we're not be able to go through all of them. Then what about the microstructures? So how that changes with the strength? So you can see that when you don't have much glutaminous here, which is you have a pretty nice aggregates here, pores as well. But when you have the a lot of aggregates here, so a lot of glutaminous inside, so you increase the concentration from 0.225 to 0.1%. So they have a big change on the aggregates. So you don't see much of aggregates there. And at the same time, you will see much finer networks. So those finer networks probably will because that you don't have a lot of interaction goes on, because the higher surface charge of proteins, they're gonna have electrostatic repulsions, and that probably weaken their gel strengths. So besides those macrostructure study, we also did a X-ray studies. So the X-ray studies, we have the ultra small angle and small angle. So ultra small angle, you will see much larger structures, while small angle, you will see a relatively smaller ones. That from a few 10 to 100 nanometers. That basically you can see from the small angle. So ultra small, you can see up to 1 microns. And we did a X-ray scattering for the gel samples, and you can see that. So this is the black one on top. This one is the control. And when you have more glutaminous inside, you will see that those intensity decreases. So those intensity decreases means that they will form a much less aggregates, which is agree with the macrostructure studies by SCM. So most likely the deamidation could help to form a final with the network. Same time it will limit this aggregation. So we want a certain amount of aggregation in order to have a decent gel strength. So the next one, so deamidation is weaken the gels. So the next one is the phenolic compounds. So phenolic compounds that you can also find in the commercial plant protein ingredients. So those metabolisms mainly exist during the protein synthesis, and some of the phenolic compounds even bind to proteins and very hard to be removed. Then we want to see how the phenolic compounds affect the gel strengths. Because if there are some ingredients that they have quite a lot of phenolic compounds or relatively higher phenolic compounds, they are probably good for antioxidants activities. But when you have a lot of them, so how they gonna affect the gel strength? For animal proteins, that they have found out that if you have some phenolic compounds, they could actually make gel stronger. But we have a different opposite finding, that if you have P polyphenols or you add additional, phenolic compounds into P proteins, most likely it will weaken the gels. So again, very similar to previous studies that we just add the phenolic compounds into P proteins, and we heat it up for 30 minutes, and we form a gel. So we look at the rheological properties and we look at gel structures, and we also look at the molecular interaction. So what kind of molecular interaction that phenolic compounds could interact with P protein, so they could make the gel weaker. So first we look at the suspensions as before, and when you have different phenolic compounds, you can see that this is the absorbance, right? The turbidity. Basically, if you have adding more grantee polyphenols, that's the full name. So grantee polyphenols, you will see that the absorbance increases. This mainly because that they probably form a larger aggregates inside. Then we want to do a centrifuge to see if they form larger aggregates, then most likely they will be easier to precipitate. And we did a centrifuge, and you can see that when you have more grantee polyphenols inside, you will see more like a more liquid phases after centrifuge, which means that they form aggregates during the mixture, right? If you add polyphenol directly into pea protein suspensions, it's gonna form those aggregates. And we also see those confocal images. You can see those larger particles. While this one without the control ones, there's no grantee polyphenols. You'll see much finer particles there. And so when they form pretty large aggregates, and they most likely they will, you don't see much of the viscosity increase. Most likely it will decrease because they will have less molecular entanglement in the suspension when you have a lot of aggregates inside. So this is the control one here, and then when you add more, it's gonna drops. So the viscosity actually drops. So that's how it look like. So after we heat it up, you can see that is the pea protein. No GDP is pH 7. So you will see that how the gel look like. It's not a very stronger gel, but if you look at the 0.5% GDP, it's more like a liquid, right? And this is relatively beta, but this one is more like a liquid. So if you want to get develop a low viscosity or a weaker, gel or fluid gels with probably adding phenolic compounds could be one of the options could be used. Then after we get the gels, we examine the storage modulus, because that will directly tell you whether the gel is stronger or weaker. And you can see that when you have more phenolic compounds to be added in the systems, you will see much lower storage modulus. At the same time, you will see the critical strength, which is the value here, that drops to here, which means that these gels are easier to be damaged or disrupted. So besides the AMPLIS suite, we also did a crippling recovery studies, and we also have the method that fit in this one. So you're more than welcome to look at the papers. So here, yeah, this one we published in Biomicromolecules. Yeah. So when you have that, you can see that when you have the control ones, you will have much less strain, which means that they are more resistant to deformation compared to the one that had 1%. So then we want to know that because of interactions, so how that changed actually was with the molecular level flexibility. Because if the molecule is more rigid, most likely you will have a stronger gel. If the molecule is more flexible, most likely the gel will be weaker because they don't have a lot of interaction there. So we did a solid state NMR for the gel samples, and then we change the contact time during the spinning process. Then we do a fitting, and that can tell us the relaxation time. The relaxation time could tell you that whether the protein backbone or protein side chain to be more flexible or less flexible after you having the grantee polyphenols. So there are 3 peaks that we picked. One is the 127 or 173 ppm. This is more about the carbonyl groups. So basically, this guy. So the carbonyl groups here, which is mainly from the peptide band, that represent the backbones. We also have the RSH groups, which also present the backbones. So you can see that the relaxation time decreases for the backbone functional groups, which means that the protein molecules, the backbones becomes much more soft, more flexible. While the side chains like CH2 or CH3, so those are the side chains. It's mainly from the amino acid residues. And when the side chains has interact with the phenolic compounds, they will become more rigid, which means less flexible. But for the gels, the backbone is the one that will dominate for the final storage modulus. So you will still see that they will be more flexible after with the interact with the phenolic compound. Then we did a microstructure study for both upper small angle X-ray scattering and SEM. So that's, you can see here, that's the phenolic compounds that you have. They form quite a lot large aggregates, but those are pretty loose structures. But they have a lot of cracks between. The cracks they are not form a consistent or continuous network. While this one for pea protein, you will see that they form a lot of more continuous network, and those aggregates, you could also find out in the X-ray studies that they form much larger ones. So because their gel networks are less continuous, so most likely they will have a softer gel. Then we want to study why this happens. So what kind of interactions it has. So with the two different studies, one is with the docking studies that for the docking study you are not be able to, like, the protein will not be able to respond after it's binding to the protein. It's more like a hard surface, right? Because we know that when the molecules, especially phenolic compounds, or like carbohydrates, when they bind to protein, the protein can respond. The conformation of protein could change. But for the with the docking studies, they don't consider that because of the limited calculation power. We did this first and want to see what roughly locations that the phenolic compound could bind. So those red ones again represent the hydrophobic regions, and blue ones are hydrophilic. You can see that the phenolic compound is mainly bound to the hydrophobic regions, well, which is not surprised because they do have quite a lot of those, those ring structures, and those ring structures are actually pretty hydrophobic. But you could also see some of them, they have the hydrogen balance as well from the proteins, like side chain residues. Then we do a molecular dynamic simulation because the docking is not a we say will not consider the change of protein conformation after it's binding to the phenolic compounds. While we did do molecular dynamic simulations, so you can see that that's the representative phenolic compounds, and the orange ones and the silver ones, those are hydrophobic or like aromatic amino acid residues. You can see that those phenolic compounds, EGCG, is mainly bound to this region, which is consistent with the docking studies. And also, so after binding to those hydrophobic regions, well, the accessible hydrophobic region from the proteins becomes less because some of them has already been taken by the EGCG. So if that's the case, most likely the hydrophobic interactions of the proteins will be less. So, and then we did that, calculation for the accessible surface areas. And we did see that when you have with GDP, you will see that the accessible surface area decreases, which means that the hydrophobic interactions between proteins becomes much less after you have the the grantee polyphenols inside. So which not surprises they form like a much weaker gel. So there's another work that that we are currently under review is how we could use this gel systems, right? We seen this phenolic compound is a bioactive compound, has antioxidant, but there are also some other compounds. They are also quite with sensitive to the environment. Well, because the gel structure, they have a lot of pores and they have a lot of places for those sensitive compound to be we say reside or located in those pores. So one work that we did a few months before, and is how we could use the gel systems as an encapsulation agent for the for the sensitive compounds or bioactive compounds. But when we include those bioactive compounds, for example, phenolic compounds, well, how that affects with gel properties, because we work on the heat state gels in here, and we know that the strength decreased. But what about the cold state gels, especially for those like heat sensitive compounds that you want to use the cold state gel rather than the heat ones? And since this work is still under review, so we're not be able to share too much in here, but we have a similar findings as the heat state gel, that if including some of the bioactive compounds, especially like phenolic based ones, and they're most likely to reduce the gel strength, make it weaker as what we see for the heat state gels. And we did do a in vitro digestion study for this as well. And when you have like adding those compounds, for example, phenolic compounds, they form those aggregates. And are they going to be, because some of them are anti-nutritional factors, will that affect the, the plant protein digestibility? That really depends. But based on our studies, the limitation is going to be limited. It's not that much as we thought. So I would like to give a summary of what we have, I mean, discussed for this talk is so if we would increase the protein-protein interactions in the gel systems, most likely we're gonna make it to be a stronger gels. So in order to like tailor or modify, I mean, proteins, maybe we can think about how we could increase the protein-protein interactions so they would be able to increase their gelling strengths. So sometimes if we send this, there's too much work done for the protein modifications, and it's easier to be done by adding like non-protein like with the ingredients to be inside. You can try to add calcium chloride or low methyl pectins as a gel, I mean, strengthens. Well, if you want to make glutaminase or some phenolic compounds, they may like negative affect the gel strengths. And also there's no direct correlations between the gel macrostructures and the gel strengths, because besides the gel macrostructures, there's another thing we need to consider is interactions. What actually dominates in it, what kind of interaction actually dominates in the gel, so that make it to form a large aggregates. For example, in phenolic compound, it forms large aggregates, but it has weaker gels. While for some other study, it did make it form larger aggregates, but has a stronger gel. So that really depends on whether those large aggregates are better connected and what kind of what those large aggregates has among themselves. They have a good like interaction or not. So that's actually something to consider if you want to explain the gel strengths. So I would like to acknowledge a lot of people, a lot of people for those, I mean, those great works. So we have, I mean, this is my group that I was taking spring 2025. And we also have some collaborators that Professor Campelena, and it's a lot of great collaborations. So we also like to acknowledge the NG5 for funding of our research, and really really helpful for us to do advance the research on plant proteins, and also with some fundings from the USDA that with the relevant the topics. So I also like to thank the audience for your time to be here and to listen to this talks. So if you have any questions, I'm happy to take. Thank you.
Awesome. Thank you so much for that. I always love seeing the group photos at the end because it's wonderful to see all the people who contribute to making this happen. So thanks for sharing that as
Yeah.
well. It's really fascinating to hear all of the different gelation conditions that your group has gone through, and all of these different factors that you've taken into account. So thanks for sharing that with us. We have quite a few questions in the chat. So I'm going to start with one from one of our participants who asked a little bit about including impurities like starches. So you spoke about obviously incorporating pectin and glutaminase and these phenols, but are there other kind of starches that you tested with that impacted the gelation?
That's a really good question. So I think starch we did use starch, but as a main components rather than as the minor components.
Mm.
So most likely you add starch, it's gonna make the consistency a little bit higher and make the gels better water holding capacity. So
Awesome.
in terms of whether that's gonna be make the gel stronger or weaker, it really depends how much you add it. If you add a small proportion, it could make gel stronger, but if you add more, most likely it will make gel weaker. And also really depends on what kind of starch you add. Some of the starch they form a pretty good gels. For some others, they have a little bit weaker gelling capacity. Yeah, it's hard. It's actually case by case, and it's hard to give a absolute answer for whether it's gonna increase or decrease. But I would say if you add starch, most likely you're gonna have a better consistency. Yeah.
Thank you for that. Building on that idea of like potentially providing a better consistency, do you have you done any research or any conjectures about how well these gels would integrate with other ingredients towards kind of building a more complex formulation for something like a product, like an alternative meat product?
We did have some works is undergoing, or we have not published is we did have some carbohydrates, polysaccharides, for example, pectins and CMC. So how they actually, affect the texturization, basically the meat animal production. So are they gonna make the fibers better? Are they gonna make the textures a little bit softer? So we did have some work that's going on, but we're not allowed to talk too much because this is recording and it's not published.
I'll have to follow up with you
Yeah,
next year
yeah,
and hear the
yeah,
rest of the answer
yeah,
to that.
yeah.
Thank you for that. We have another question asking about comparison to animal-based proteins. So when we think about plant-based proteins, in comparison to these animal-based proteins, what are some of the biggest challenges that they face, in particular with regards to things like digestibility?
Um, that's a really good question. So the digestibility, yeah, the digestibility is sometimes it depends on the solubility and how easy that enzyme could get contact with the plant proteins. So because they have a different phases, right? Because enzymes are actually more soluble in the gastric or in the GI like fluid, while the protein is not always the case. So
Mm.
sometimes they are located in different phases, and that actually makes the digestion to be a little bit challenging. And another one is the plant protein, they have a lot of other impurities there. Some of them are anti-nutritional factors. So those anti-nutritional factors are sometimes, I mean, they're bound to the plant proteins and they're hard to be removed. So when they are there, that's why the enzymes not be able to get them to be very good digested. So yeah, they do have some with the because that's the protein, that's the protein, right? That's how the nature synthesize the plant protein in terms of their surface property, in terms of their they coexist with the anti-nutritional factors. So that's something that it's hard to do from the processing part, but you can try to do a little bit extraction or using some other ways to remove of some of those phytochemicals. But again, if you do that, the cost is gonna increases. So enzyme hydrolysis is gonna be a with a more feasible strategy to make it more, I mean, digestible. Yeah, I would say this way. Yeah.
Thank you for that. I think you answered some of this question already, but building on that thread of digestibility, there's another question from Alexis about any specific metabolic effect of digestive gut microbiota on this gel, and if there's how that can change the nature or role of these gels.
Um, that's a really good question. So no, I don't work with microbiota, but I could be wrong, but I'm gonna share what I saw. So um, plant proteins, we say they have about 65 to 80% of digestibility. So the rest, 25%, 20%,
Mm.
where are they? So they do have some. There are some like in the plant protein. We say that in dietary fibers has done something to the gut microbiota, but there should be some work or the starting of some work on studying how the plant proteins, non-digestible plant protein affects on the gut microbiota. Yeah. So I don't work too much on that, but that's very interesting things to explore. So how does non-digested like proteins affect the gut microbiota profile?
More questions for future work. Thank you for
Yeah.
taking a stab at that. We have a question about the feasibility of these gels in things like cell culture and tissue engineering. So, building on your work with plant protein gels, how feasible do you see their application being for things like cell culture, tissue engineered scaffolds, for cultivated meat? And given the typical low solubility and phase separation challenges of plant proteins, can we realistically control protein distribution and mechanical uniformity in 3D cast or printed scaffolds derived from these gels? Bit of a mouthful.
Yeah, I think the main challenge is if you want to make the cell culture, especially cell culture meat, you want them to be a better aligned, right? And that's something that is normally highly recommended. So the collagens, we say the collagen gels, the collagen they're good substrates because they're fiber structures, so you can easily orientate them. For those plant protein, they are more like globular gels. So you can make them a little bit anisotropic using some like shear other cells and quickly fix it. And if you want to make it to be a cell culture meat, most likely they will. You don't want them to you don't want them to be swollen too much, and you want them to be a little bit more resistant. So what you can either do a coating on the surface, or you can use some native cross linkers to make the gel a little bit stronger. And in this way, you probably can make it as a substrate. I don't know how good, how bad it's gonna be, but there are some native cross linkers. So we have another work that's under review by hydrocolloids that we're working on some native cross linkers, food grade ones. So you can actually, they could help to form those chemical cross links inside the proteins, inside like plant protein, like pea proteins. So they will make it much stronger and more like a chemical, I mean, cross linkers, but they're much stronger. So in this way, you can solve the, you can play around with the hardness or softness on the interface between the cells and the gels. And in this way, you probably can get what you want. Because I think that when the gels, when the cells start to grow, or for the cell culture meat, they have a certain requirement on the hardness of the surfaces. That's, and I don't work much on that, but sometimes I read a little bit. Yeah, I would say this is probably you can consider, yeah, to introduce different like cross linkers, a different degree of cross linking in the plant protein gel to make them like reasonable hardness that suitable for cells. You could also incorporate some of the nutrients in the gels so they could slowly release during the processes. Yeah.
It sounds like a very promising future research direction. So all of you in the audience, keep that in mind. Um, Obviously, like you did a great job articulating the importance of these protein-protein interactions. And I'm curious about if you have done any research about kind of blending different proteins or bringing together kind of proteins outside of just pea protein to potentially increase the functionality or tune the gel in that way.
We work a little bit on the soil, and we started work on canola, and um, since different proteins are so different, and it's hard to find, the common sense. For example, we also work a little bit before, but that was just some kind of interest. Some Q1 proteins. We know that Q1 protein has a really strong gelling capacity compared to peas. Um, but we didn't do much because of we have some other projects that's going on. So we for the hydrogen gels that we don't mix with other plant proteins so far. We only work on the pure single system. The reason that is easier to interpret for the results. But for the meat analogs, we are trying to work with a mixture of different type of proteins to see how that affects the texturization and meat analog textures in some other sense. Yeah.
Awesome. Thank you for that. We have another audience question here about if you have analyzed specific chemical or enzymatic modifications to the protein surface that could increase gel strength.
Chemical chemical modifications. Yeah, chemical is pretty broad. You have the acylation, you have phosphorylation, or you have the we work on deamidation, one of the chemical modification, but it was done by enzyme. You could also use like sodium hydroxide to do that. It didn't increase the gel strength. It's because deamidation makes it more charged. So it's hard to say. I mean, but my personal view is it's gonna be not that promising because if you add a lot of interactions there, just like, if there are electrostatic repulsions, then it's gonna make things worse, right? Because the protein does not able to come close to each other. And if you add a little bit, if you make the surface a little bit more hydrophobic, that could be, I would say worthwhile to try it, because you will change the balances between the surface hydrophilicity and surface hydrophobicity if you add some of the hydrophobic groups, and that potentially will facilitate more hydrophobic interactions. Yeah, we have not done any, other, like, we say isolation or some other chemical modifications on the protein. Is because we find is, the solvent we use is sometimes not food grade, and it actually makes we say industries, people or customers, I mean, scare away, because yes, sometimes we say it works really well, but it's no cannot be practical applied. It's because there are a lot of things are not food grade. So most likely we try to do things that can be done in food grade. Yeah.
That makes a lot of sense. Thank you for that. We have another audience member asking if you could elaborate a little bit on our earlier discussion about starches, and specifically talk more about how starch affects the viscoelasticity of protein gels.
Yeah. That's a good question. So because we're more talking about based on the predictions. We haven't done any work on the starch protein gels. The reason that so first, I think we're gonna for the viscoelasticity. So first, we're going to look at the how strong the starch gels and how strong the protein gels at the same solid content. Because if you plan to mix the two, they could make, they have scenarios and that you can make it stronger. But sometimes if they have too much phase separations, because proteins, especially plant proteins, they are more hydrophobic. So if you look at the pectins and protein work that we did before, and they are actually, phase separated. So if you have too much separations there, most likely you will make the viscoelasticity decrease. But if you have a reasonable, or you can control a lower amount, you can actually make it gel a little bit stronger. So that's why I say it's gonna it varies with the proportions, and also, like, what kind of starch, what type of starch used. And so proteins, they don't, especially plant proteins, they don't interact too much with starch. So they are, because they are most likely just to be after you gelatinous starch, right? You get aminopectins. So they maybe have a little bit hydrophobic, but majority of them were gonna be the hydrogen bondings. So they don't have much strong, like, for example, ionic interactions or electrostatic interaction. They don't have that much, because starch, we call it, is a neutral molecule. I know there are some charged stuff on the starch, or you can use modified starch. Probably they will be working better if you could introduce a little bit charge on the starch using modified ones. Then that will be more promise compared using the native starch.
It seems like a really broad space to explore for
Yeah.
sure. Um, this is a bit of an out there question, but I know there's a lot of research interest in thinking about reversibility of gels and things like that. Do you have any thoughts on kind of a path towards something that has reversible gelation, using some of the ingredients like pea protein that you mentioned here?
Reversible gels. That's a really good question. I never thought about that. So um yeah, that refers for the plant proteins. So for the plant proteins, like, the reversible is mainly that majority of the systems is non-covalent interactions. And when you do something, so those non-covalent interactions are easier to band, are easier to dissociate. And then when you like, remove those, some, for example, you cool it down, it will be back again. Well, it's not as what we expected, because what we saw that will be happening a lot. Yes, it has non-covalent interactions, but when the non-covalent interaction has a lot, for example, that cellulose, right? They are non-covalent interacts. They have a lot of hydrogen bondings, but they have a lot of them, so that will make them like very very robust. So you probably can do that for the weak point of the protein networks that they probably can disassociate if you do some like heating other things. But for some other parts that they have quite a lot of non-covalent interactions, I wouldn't say that would be very promising to go back to its original. You may get a little bit less viscoelasticity, but it will not as like as a solution. Yeah, but some others like this is not like like proteins is not like carbohydrate based gel that you can like lower pH it will gel, and increase the pH it will be liquid. For plant proteins, unless your gels is mediated by a very single interactions. For example, if you use ionic, calcium ionic stuff, that very single ones, and you can easily remove those stuff to break those single interactions. Otherwise, if you have multiple like multiple type of non-covalent interaction inside, it's gonna be, I guess, gonna be pretty challenging. Yeah.
I think that makes a lot of sense. Thank you for thinking through that with me. We have another audience question here. Do you work with animal and plant hybrid protein systems? And if so, do you think it could be, or even if not, do you think it could be a good way to solve some of the challenges, such as the protein solubility challenges that we've discussed?
Um, we have not worked on, as at least as a principal investigator, I have not worked on mixed systems of animal and plant proteins. But when I was a co-author, I did involve in some of the work. Sometimes the reason that I didn't work on that is because it's hard to locate, it belongs to, because plant protein field, and they want to be pretty plant-based, and animal-based ones they're to be more like animal-based. So you're gonna annoy both sides basically. But for the gel systems, we did work on one. Sorry, I did work on one, which is the cream cheese, right? But that's not a very typical hydrogels. That's more like a cheese a mixed products. So and in that research, we're using the pea proteins as a replacement for the animal feed, which is a very small proportions. I would say majority of the protein will be plant. It will be dairy, and a small portion will be plant. I wouldn't call that much a kind of mixture. It's a mixture, but it's not as a decent proportions. So yeah, if you mix the two, it could. So if you add a little bit animal proteins to like plant proteins for the pea protein, you could make it just stronger, because you will introduce a bit more covalent interaction for sure. Because for example, whey proteins, when you add it, you'll make stronger gel because you will form more covalent interactions. So that could solve make the pea protein gel a little bit stronger and more better digestible, because we have more animal proteins. That is like 95 to 100% of digestibility. Yeah, you can solve some of the challenges. Yeah, at the same time you're gonna, yeah, it's a sentence. Yeah, for an industry probably they can do that, but for research sometimes if you apply for some proposals, if they have certain requirement on pure systems or only from plant, then yeah,
Could be a challenge for
yeah, it
sure.
can be challenged. Yeah.
Well, thank you so much for engaging with all of these questions and for your wonderful talk. Good luck with the end of the year. We really appreciate you joining us today.
Yeah, it's happy to be here, and it's happy to interact with you and some other audiences. Yeah, it's great.
Awesome. Thank you so much. And thank you to all of our audience members. We'll see you next month for our last Science of All Protein seminar of the year. Thanks, everyone.
Yeah. Okay. Bye bye.